Started the... okay. Yes.
There's something, no, it's okay.
And I already said yes. It's fine. Okay. Thanks a lot. So I'm very happy to be here. So I'm a researcher at Inria, so next door, right? 5 minutes from here. And I'm creating soon a group with Filippo Vicentini and Tito Carret between Inria and Polytechnique, both the computer science department and the physics department. And we are creating a group working in quantum information theory, quantum computing, quantum communications, and also quantum simulation, so simulating quantum systems. And yes, so today what I will do is to present one of my work with colleagues in well, mainly Geneva and Vienna and Spain, Barcelona, on the role of complex numbers in quantum information theory. And so this result is can really be seen as a generalization of what we call the Bell theorem, which is something very fundamental for information theory. So I will first present what is the Bell theorem, try to explain it, and then I will go to our results, and hopefully this will work. Yes. So to explain the Bell theorem, I will first come back to what we call the Schrödinger cat paradox, which is dead and alive. So I will explain what we mean by a cat which is dead and alive. Okay, and to explain that, I will come back to the double slit experiment. So the double slit experiment is the following experiment where we have a source of light, and this source of light emits particles of light, photons one by one. So this is something important. And then there is a string with two holes. So the photons can pass either through the first or the second. And then there is a second string where we just accumulate light and see what's going on. Okay. And the question is, what should we observe? And we'll try to make some logical deduction about this experiment. And so we'll make the following assumptions. So the first one is really that the source will send photons one by one, and that the photons will take some reasonable, let's say, more or less straight line trajectories. A second assumption, and actually it's an observation, we can really do the experiment, is that if we had one hole, then we would see something like this. So you see the photons are arriving one by one, and we see more or less a central spot. And then, so I will represent the central spot like this on the screen. And then the last assumption is that we can use the logical OR. So the logical OR just tells us that the photon will take path up or path down before going to the screen. Okay, so now let us do some deductions from that. So when we have the two holes, we could imagine that actually we block the first one. And then, as there is one hole only, we should see just a spot there. If we block the second, we should see a spot, another spot. And then if we block nothing, we use the logical OR, right? So the photons one by one, and we take either this hole, and then we see this, or that one, and then we see that. So when we don't block anything, we should see that. Okay. Actually, if we make the experiment, this is what we observe. So we observe what we call fringe of interference. So we don't observe at all what we have deduced. Okay, so if I represent it on the screen, it really looks like this, right? Or like that. So that's a bit problematic, right? So of course, if our conclusion is not true, it means that one of our assumptions was wrong. So it can be either 1, 2, but 2 is just an observation in the end. So it can be either 1 or 3, which is wrong. So we'll first review quantum theory and try to interpret what quantum theory tells us about what's wrong. And then what quantum information theory tells us, if we look at the formalism, is more or less that 3 is wrong, right? One cannot say after the photon arrived on the last screen that it took the path up or the path down. This sentence is just wrong. Okay. And then actually quantum information theory somehow introduced a new concept, which is you are not allowed to say or, right? So you have two choices, but you are not allowed to say or. So this is why we invented this word the sentence, the photon took path up and path down. So what is really important about this and is that it has no content. Somehow it's just there to stress the fact that we are not allowed to use or anymore. Okay, so when we say and, actually it's to say, be careful, you are not allowed to use or, and there is no other meaning to this word. So, well, a good question is, should we accept this, right? It looks a bit crazy. And actually, a lot of people have problem with this. So there is this famous EPR paper in 35 where they describe this, well, in a different context, but somehow it's the same problem. And they said, okay, we don't want to accept this, and we should find alternative explanations, which would be, again, compatible with R, and which would explain, for instance, these observations. And then the question is here, can I find alternative explanations? And then actually it's very easy to invent new explanations where we will be able to find something compatible with R again, just by rejecting one. So I could imagine that actually my photons are just a little space shift with a small creature in it. And then this space shift just drives everywhere in the space and looks at the first hole, pass through it, and then come back, maybe check if the second hole is blocked or not, and then depending on all this information, just decide where to crash on the screen. And obviously, as it will accumulate all the information, this spaceship can create fringes when there are two holes and just one slot when there is one hole. Or we could say that actually it's not photons, they split in two, they interact with their paths, etc. So this is a bit far-fetched, but it works perfectly well logically, right? So the question in the Bell theorem is actually, can we always find such a, let's call it far-fetched explanation, or are there situations in which actually there is no way to find a far-fetched explanation of that? And this is all the content of the Bell theorem, is to find some context in which it's impossible to find such a far-fetched explanation. So let me go now to the Bell theorem and explain why in this new experimental situation, we have the same problem about the logical R, but there will be no way to find something compatible with it. So the goal here is to really find a situation which is not compatible with this R. And the way I will formalize this question is as a challenge between an experimentalist and a detective. So as an experimentalist, I will take Alain Aspect, who obtained the Nobel Prize because, well, he actually implemented the experiment I will review. And I will take as a detective Einstein, who really questioned this logical problem of quantum theory not compatible with the logical part. And then, so the detective believes in some classical principles. So the first principle of the detective is that the logical R can always be applied on unknown information. So if in the universe I have somewhere a box which contains some unknown information, I will always be able to say this box contains the information lambda1 or lambda2 or lambda3. And if I go through all potential value of that information, I capture the reality of the information in that box. So when I take this situation of the photon going either on the top or bottom hole, right? I could say that I have a box, right, which contains some information. Lambda1, the photon went up, or lambda2, the photon went down. So more generally, now if I don't know at all what's going on in the box, I could say that the photon will take path 1, or path 2, or path 3, or, right? There may be infinitely many paths, but I can always say that. And then the second assumption of the detective is that information carriers do not travel faster than light. So this is something very fundamental in physics, in relativity, the fact that, okay, I cannot travel faster than light if I carry some information. And this is a very important assumption because it will forbid actually the photons to explore all the space, which the photon was doing in my far-fetched explanations. So these are the two main classical principles of the detective, and then the experimentalist, so of course agrees with two that believe that one is wrong because he believes in quantum theory, and he will construct a concrete experiment associated to some observations. So in quantum theory, we write these observations like this, but I will not enter into the detail, it's not so important. And then the detective will try to explain his observed experimental results, allowing himself for any far-fetched explanation compatible with these two principles, and he will fail. He will not be able to explain the observations from the experimentalist experiment. So it was just to present the overview. Now I will go more into the concrete theorem. And so first I want to show you that it's something actually very concrete, that there are experiments. So this is the picture of one of these experiments where you have a two-photon source. So in quantum theory, we write it like this, but it's not so important. So in this picture, you have to imagine that you have a source of two photons somewhere in the middle. And then the two photons are driven in two different places. So here there is Alice, here there is Bob. And then, so this is the experiment, and the detective looks at it, but the detective does not trust anything about it, does not know what are photons. So we just model it as, two boxes, one for A, one for B. And in A, I have some choices of experiment I can do, and I observe some results, and the same for B. And this is all what the detective trusts, right? So, okay, let's assume, so I recently did that talk in Strasbourg and I didn't have time to change that, but let's assume that Alice is in Strasbourg and Bob in Saclay, right? On my picture, it was a few meters, but the experiment should work also if I have several hundred of kilometers. And then, so this is really how the detective will observe the experiment and what he will see and how he will deduce stuff. So let me drive you through the deduction of the detective. So, he will look at the experiment going on many times, right? So there will be many different rounds of the experiment. And at each round, there is some value of X. So what choice of measurement to do on this side of the experiment, which will be selected, some for Y. And then we will observe some method A and some method B. And we'll do it many times, right? And accumulate statistics like this. And then to characterize these statistics, what we do is that we look at some specific, what we call score. And the score is the following. If X is equal to Y is equal to 1, what we want is that A is different from B. And if it's the case, we just count the score 1 for this try. And if X and Y are not in this case, we ask that A is equal to B. And again, we count the score 1. And if this is not satisfied, we count the score equal to 1. Okay? So I just play the experiment many times, and I look each time at the score, and I just look at the mean score, which is the limit when I have performed this experiment many, many times. So for simplicity, let's say that we play this infinitely many times, and we look at the limiting score. And what the detective sees is just that this score is 85%, more or less. Okay? It's a rounded value. Okay, so you are the detective. This is an observation, right? And you have to explain this observation. And you see some correlation in what's happening in Alice's side and Bob's side. And quite fundamentally in physics, when you have some correlations, you have two possibilities to explain them. Either you have an influence from one device to another, or you have an unknown common cause. So an influence would be just, when Alice selects X number 0, then there is some electromagnetic signal traveling to Bob's device, hitting Bob's device and changing the behavior of Bob's device and deciding maybe the value of it. Okay. And then a common cause would be, well, actually 0 and 1, for instance, the output are just the experiment worked or did not work. And then maybe, when it's raining, the experiment is not working because the devices are not working when it's raining. And when it's sunny, it's working. And as the meteo in Strasbourg and in Saclay are quite similar, right? It's an unknown common cause. Then it's not working in A and in B with high probability at the same time. So these are the two main possibilities. Well, these are the only two possibilities to explain these correlations. And then if I have an explanation like this, it's very easy to get a score even 1, right? Because in that case, the value of X and maybe of A also will be sent to B, and I can always adapt this B to obtain a score. In that case, it's a bit more difficult. So if we try it, and if we look at the score and we assume that X and Y are selected completely at random, well, what we see is that this case will happen with probability 1/4. And these cases will happen with probability 3/4, right? Because there are 4 possibilities for x and y. So if I just ask A and B to be always equal to 0, I will win in these cases and I will lose in that cases. So I will obtain a score of 75%, right? It's clear for everyone that 75% is very easy to obtain, right? Is there a question online? Okay. So 75% is very easy. There are many ways to do it, but it's not so clear how to obtain more. Okay, so then there is a very important assumption, which is this fact that information cannot travel faster than light. So you see that for the influence to go from A to B, it takes time because there is some distance and it cannot travel faster than light. So what is important is that these experiments are very well synchronized. So X is chosen at random, and at the same time, almost B appears. So with this, we are able to rule out this kind of explanation because there is no time for the influence, for the value of X to hit both devices. The output B has already been created. So we are sure that we are not in that case, and the detective really can deduce that he is in that case, just because of synchronization and his second assumption. So then we are in that case, but we see 85%. It's easy to do 75, but how to do 85%? What I will show you actually is that it's completely impossible. So, of course, if the experimentalist is looking at the detective making some deduction, he will agree with this first deduction of the detective because he placed a common cause to the two parties. What is important to have in mind is that the detective does not believe in a source of photon correlating these two devices. He just deduced that somewhere in the universe there is some unknown common cause, which explains my correlation, but it could be anything, right? Seismic vibrations, the meteor, cosmic rays, whatever it is the common cause. There must be a common cause from. Okay, so let me continue with the detective deductions. So now I'm back to the situation where I have a box somewhere in the universe containing some information, which I will call lambda, and which decides what happens then, what are the correlations between A and B. So I really have a value lambda1 or lambda2 or etc. in this box, taking some different probabilities. And then what happens is that A will just be a function of this X and this value of lambda, and B will be a function of B and of Y and the value of lambda. Of course, A cannot be a function of Y because has no Y, the value of Y has no time to travel to A. And then if I compute the probability distribution over AB given XY, in this experiment will just be the sum of the all potential value of lambda of the probability of lambda times the probability of obtaining A given X lambda and the probability of obtaining B given X lambda, right? So from my model, it's a direct mathematical deduction. It's quite trivial, so like this. So of course, the experimentalist will disagree with this because for him, a box containing some information, I'm not allowed to use OR to describe it. And to write this, I really use OR, right? Or this formula. And then, so there is the Bell theorem, which just says that once we have written this formula, with such a probability, it's completely impossible to obtain some value of S, which is larger than 0.75%. So my naive strategy from the beginning is really optimal. And mathematically, it's pretty easy to prove. You see that this is just a linear combination, right? So I have a polytope somewhere, I can just look at deterministic strategy. So, okay, I won't make the proof, but what I want to say is that the mathematical proof of all these are all trivial. The problem is conceptual, but all the math are high school level, right? Okay. And then, so what happens is that there is a quantum strategy which the experimentalist will follow, which will be able to obtain this exact value, so a score of more or less 85%. So it's not so important how the how the experimentalist obtains that, right? If you know quantum theory, it's just some mathematical expression in the formalism of quantum theory. But really what is important to understand is that the proof of the Bell theorem to understand it, you have to think that you are this detective in front of the experiment. And there is no need at all to understand what quantum theory is about. All what happens is that you see some experiments, you see some statistics, you have your assumptions, which are standard classical assumptions, and you see that there is something you cannot explain, right? So the detective does not know what is quantum theory, but he still has a problem. What is that problem? It is that there exists some situations in which the logical OR cannot be applied. Okay. So this theorem is really about what cannot explain the predictions of quantum theory. The logical OR cannot, so there does not exist any theory, any explanation of this concrete experiment which we observe, which can be compatible with the logical OR. Okay. Maybe let me do, I didn't say, if you want to interrupt me at any moment, it's completely fine. So maybe I make a small break if you have questions. Now I'm very happy to answer it.
Some question on the bridge also? Everything is clear?
Yes. So
I have problem with the quantum information theory, because what you explained about the double
slit experiment.
slit experiment is quantum physics.
Yes, indeed.
So
Indeed.
information theory has been invented far later, and
Well, okay.
So the
No,
problem-
I wanted to give a physical like intuition of the problem. Indeed, yes.
Oh, in fact, I want to say, since I have to, I will participate to PhD I'm happy to be involved because I will be able to put in my objective quantum network, and this is good for me. So, but just I wanted to
Okay.
to be sure that there is no risk of losing people on the term quantum information theory, which in general is more related to quantum to information system based on quantum system, which is like the quantum computer, quantum simulator.
Okay. Okay, so let me continue. So I presented the Bell theorem. So again, this theorem is mathematically trivial, right? So to prove it mathematically, you do trivial math. However, it's really more philosophically extremely problematic, right? And most often, when you have seen it for the first time, you don't accept it, right? And it's normal. And this is the problem. The problem is to accept it philosophically. The math, you have understood everything, and it's really trivial. So if you have the feeling you have not understood it, actually, you have understood the math, right? It's more that it's hard to accept. So now I want to discuss the implication of the Bell theorem. So again, what I said is that the Bell theorem is not about quantum theory. It's about all potential theory which would replace in the future quantum theory. And it says that any such potential theory of information cannot be compatible with the logical part. So now what I will do is to show you that actually I can make this type of deduction for a lot of properties. So what I say is that, okay, it's incompatible with this logical OR. What I will show also is that any such futuristic theory will not allow for cloning of information. I can prove that. And I will also, so you can prove this. I will not go into the details. I can also prove that any such theory will be intrinsically non-deterministic. Okay. And then, no, sorry. So these are properties of quantum information theory. And then there are corollaries of the Bell theorem, which are that all these properties will be somehow conserved by any futuristic theory which would replace quantum theory. So any futuristic such theory will be incompatible with the logical OR, will not allow for cloning of information, and will allow for what I call randomness amplification, or will be either deterministic, non-deterministic, of super deterministic. So I will not go into the details, but you will have a notion of intrinsically non-deterministic. And then all these corollaries, actually, they have direct applications. So from these properties, you can find protocols which will work with fully uncharacterized devices. And this will allow for quantum K distribution or quantum random number generation just by looking at the statistics of your experiment. So what is really important here is that it goes way further than the, for instance, BB84 protocol. There, what we will obtain is some quantum K distribution where I don't need to trust at all my physical devices. All what I will check is the statistics. Just by looking at the statistics, I will know that my devices are working as they should. For instance, I will know that there cannot be cloning of information. And in a cryptographic protocol, typically the attack is to clone the message on its way from Alice to Bob in order to read it. And this is fundamentally impossible from the correlation. So I don't have time to go into all this. I want to stay at the theoretical high level. So I will show you that actually from the base theorem, I can show that there cannot be any cloning of information. So let me try to conceptualize the question a bit by conceptualizing what is a cloner for me. So imagine that I have a causal process in which I have somewhere a particle carrying some information which is created, then sent somewhere else and measured to find that information. So now what I call a cloner is just something that I would insert on the way of the particle, which would create two particles, such that if I take duplicate of that detector and place them like this, and if I forget about the second detector, what I see between this and that is exactly the same as what I see there. And if I forget about the first detector, what I see between this and that is exactly what I see there. So this is just a cloner form. So in quantum theory, it's quite easy to show that such a cloner cannot exist if you write the mathematical formalism, but not interested in this. I'm interested in any futuristic reasonable theory of information. And what I will show is that, again, it cannot exist. So I will imagine that I have a weird theory, right? And weird detectors and weird way to clone the information, and I will show that there is a problem. And how do I do that? I will do a proof by contradiction, and I will start again from the CFSHD. So I will start from this experiment, which was created by the experimentalist, where I see a score of 85%. And I will assume that I can explain this in my futuristic theory with this weird sourcing, where I can clone information. And then I will clone the information, right? So I will insert the cloner here. Okay. So now what I obtain is a situation where I have A, B1, and B2. So actually, you will really see that this is computer science, it's not physics, it's really a computer science. So I have A, B1, B2, and then, so from my assumption of a perfect cloner, if I forget about B2, I have that this score is satisfied between A, B1, Y1, and X, right? Because it's a perfect cloner. And the same is true between A and B2, okay? So I should observe this score between these bits, right? Which is equal to 85%, and this one also. And then, okay, so I will use this as, let's say, an oracle to reconstruct something else. And what I will imagine is that I place now B1 and B2 in a single room, right? So Alice is in Strasbourg and B1 and B2 are in Saclay, they are together. And I will ask B1 to always input 0 and B2 to always input 1. And then I will output the sum modulo 2 of these two bits, right? Beta, which is just the sum. And then, so again, I will not make the proof, but it's really trivial to show that actually beta contains some information about X. It's trivial to show that beta will contain some information about X in the future. Just from the fact that this score is 85% and this one is. And this is really problematic because it's violating our second principle, which is fundamentally in physics, really fundamental in physics, which is that information cannot travel instantaneously. And here I have a situation where X, Alice can select some X, either 0 or 1, and instantaneously you have some information about the choice of Alice somewhere else in the universe. And this is completely forbidden from very basic physics principle. It's not reasonable at all. So what I have shown is that if there existed some cloner in my theory, if I could universally clone information, I would have a problem. It would be incompatible with the fact that I can observe 85% of the experiment was already there. So if you go a bit beyond that, you can really show that the limiting score is exactly 75%. So if you are below 75%,
may I ask a question?
yeah, of course, of course.
So here we may suppose that we measure exactly without error 0.85, but usually we may have some errors and we don't know. It's a bit, it may be a bit lower what we measure, maybe 0.24 or 23.
24, maybe
80,
right?
80, so something a bit
Yeah.
lower. But then the proof, yeah, this is what you want, I think.
It's exactly what I
It is
mean.
all the-
If you are above
if you-
75%, there is.
Sorry, I
still a
didn't
problem.
write it. Okay.
Yes. So 75% is really the limit, right? Where you can start to clone, but it's classical information you can clone.
That's why you can even prove more. You can prove that it is possible to clone even approximately.
Yes,
Yeah,
yeah, of course.
Okay.
No, but okay, I just want to give the high level principles, right? I don't know.
It was more detailed the question
Yes.
for myself.
But
Okay.
there is possibility to clone approximately, but with epsilon chance to fail. So
Yeah, well, you have a lot of subtleties, but at the very deep level, this is really what you have, then you can try to be more technical and understand more details. Okay, so I'm done with the second part. So yes, what I really wanted to tell you is that this idea of the logical OR, actually, you can generalize it to a lot of stuff, right? So cloning of information, determinism, and it's directly associated to also concrete protocols. So if you want to do cryptography, directly from the Bell's theorem, you have something very fundamental, which is that just by looking at statistics, you can know that your protocol is secure and nobody is trying to clone the information to eavesdrop on the message you are trying to send. Okay, so now the last part of my talk is about this work. So quantum theory with real numbers is incompatible with quantum theory predictions, which is just a generalized Bell theorem. So I will explain what I mean by this and what is the result exactly about. So let me go quickly back on the Bell theorem. So the Bell theorem, I presented it as a challenge between an experimentalist and a detective building in the logical OR, where the experimentalist finds a good game. So a good game is a game where he finds a star which cannot be explained by the theory of the detective or the family of theories of the detective. So now what I will do is just to generalize it. So I will remove this detective theory and I will change it into a different theory. Okay, so instead of a theory, considering a theory compatible with the logical or maybe a theory compatible with cloning of information, I will look at some other theory. So now, of course, if I am in this situation, so I will specify the theory after, what I want is to find a good game where the detective fails, right? So I will do this with what we call real quantum theory. So let me first present what is real quantum theory. So I'm sorry, I have one technical slide, but it's important to do that. So I don't know actually who knows the quantum formalism here. Okay, good. No, there is no problem at all. In the quantum formalism, you have, I guess you know that it's matrices in Hilbert spaces, right? So you just have Hilbert spaces, you have matrices, you ask these matrices to be positive. And what is important is that you have a way to describe what is a state, so some information which is created by someone. You have a way to describe what is a measurement. So this is how we try to measure that information. And you have then, once you are given a state and the way you measure it, you have just a rule which will tell you what is the probability of obtaining this result or that result. Okay. And all this is written in terms of matrices, which are positive in some Hilbert spaces. And what is very important is that at the fundamental level of the axiom, these Hilbert spaces are complex numbers. Okay. And then there is a second last very important rule, which is now if I have two states, so two particles carrying each some information, the way I would describe the two particles is in a tensor product of the two initial Hilbert spaces. Okay. So these are the axioms of, so it's quantum information theory, it's not quantum mechanics, because I'm just talking about how information can be carried by particles. I'm not talking about how these states evolve. I don't have any Schrödinger equation, what we call the Schrödinger equation. So if you want, in Newton's mechanic, you have the cinematics, which is how do I describe points moving in the universe? And you have the equation of evolution, Newton's law, which tells you, depending on where are the masses, where this point will move, right?
It is the density operator in this point.
Yes.
Okay.
So here I'm just talking about the cinematics. I'm not talking about the dynamics, how things will move, because I should give the Schrödinger. So it's really information. I'm not considering how I create these states physically in practice or how they will evolve in practice. Okay, so now what is the theory of the detective? The theory of the detective is exactly the same. So I take the same axioms, but now instead of complex, I replace it by real. Okay, and that's it. No more.
That's like Markov theory.
No, I just replace it by R. Okay. So something which is really important is that the question we are asking is not about asking the question, is it possible to have a theory based on real number which explains this quantum theory? Because in that case, the answer would be obviously yes. You have a lot of theories actually, which are written in terms of real number, which can describe all quantum phenomena. Or more generally, what we could say is that here, when we talk about theory, we are just considering the description of all the observations which can be done in all potential experiments in terms of probability distribution. So remember this Bell experiment, I have A, B, and I compute some probability distribution over the outputs given the potential inputs. So this can be debated, but if I pretended that a book containing all the observed probabilities for all the potential experiments, so I have an extremely large book with two columns. On the left, a drawing of all potential experiments. On the right, a description of all the probability distribution over the statistics I will observe, right? This, of course, only contains probabilities, so real number, and it's something I could call the theory which describes my experiment. So there are a lot of ways to describe quantum mechanics with real numbers, but here, what I'm talking about is the precise theory, which is written in terms of these Hilbert spaces, these density matrices, these structures, and the tensor product rule when I have two particles. Okay, maybe I will jump over that. So there were already arguments rejecting that theory, but we go beyond that. And I will directly move to the game. So what I will first present are some games where the detective will win. So there will always be a way for the detective to explain the experiment constructed by the experimentalist. So I will first consider that game, and this is the most important game to understand what I'm talking about in this last part of my talk, because it will really give all the intuitions for the remaining of my talk. So imagine that the experimentalist tries to tell the detective, look, you are wrong because you are not able to explain the statistics of this experiment where I create some state, I measure it according to some input, and I obtain some outputs, and I observe some probability distribution. So the question for the experimentalist would be to find a good state and a good measurement such that this cannot be simulated. So actually, this can always be simulated, and I will explain how. So I will first explain it in the formalism. So for most of you, it is not so useful. So you should maybe rest during 30 seconds. And then I will try to explain with the hands what's going on and how is the simulation of the detective. So now I really talk about the formalism, and I will give the intuition after about what it means. So in the formalism, the way the detective can always simulate this type of experiment is to introduce an additional state, an additional qubit, which I will consider in two states, I or minus I, which are this and that, right? Where clearly this is the complex conjugate of that. And then what the detective will do to simulate any of such experiments is just to consider a new state. So if I start from rho, I will consider the new state rho tilde, which is just the convex mixture of rho tensor I plus rho star tensor minus. And then I do the same for the measurement operator. And then it's very easy to show that actually the operator is real, because if I complex conjugate it, I will exchange these two terms, so I find it unchanged. Okay, so now let me explain with the hands what's going on. So the experimentalist is proposing some experiment where he says, okay, I will create that state, which is complex, because of course I want to show that in the end there is no way to represent it with real number. So in the formalism, this is just a matrix of complex numbers. It's a 5 by 5 matrix of complex numbers with different entries. And then I will measure with some operators, some measurement operators. So again, it's some 5 by 5 matrices. Okay. And the experimentalist proposes that experiment and hopes that there is no real way to explain these observations. Okay. So this probability to compute it, you just take some trace of this matrix and this matrix where there is this technical formula. And then the goal for the detective is to find a simulation of that in terms now of real matrices. So with this formula, I'm just giving you a new way to start from that 5 by 5 matrix and create. So now it will be actually a 10 by 10 matrix, which is real now. And also, I will give you some 10 by 10 measurement matrices, which are also real, such that in the end, this probability distribution is constant. And this makes a lot of sense, right? Because if I want to encode one complex number, I need two reals. I'm doubling the dimension. This looks quite intuitive. Okay, so it corresponds to this standard intuition. And then I can try to interpret a bit more what's going on. So the point of view, so how do I construct this? So the way I construct it, the way to interpret it when we know what is complex quantum theory. So it's an interpretation which is done by the experimentalist is actually what the detective is considering is a new physical system, which is composed of my old dimension 5 particle, this dot, right? To which I have added an extra particle, which is just a qubit, the generalization of a bit, which carries a bit of information, which is this small triangle. And this small triangle carries some information, which is the information, what is the value of the square root of -1? So anytime the detective wants to model some experiment with the particle of dimension, let's say 5, he will use some system of dimension 10, and this system of dimension 10 will be composed of the old system of dimension 5 plus an additional system of dimension 2, so a bit of information which contains the information, what is the value of square root of -2. And this particle will alternate with pretty 1/2, 1/2 between the value plus I and minus I. And as we are alternating with equal weights, actually the complex numbers vanish. Okay? So somehow in my system, there is really a flag indicating to this box what is the value of the square root of -1. And then the measurement will first measure the flag. And if the value is plus I, it will apply the standard table of numbers. And if the value is minus I, it will just take the conjugate of each of these numbers, so the new table with the conjugates, and obtain the same probability. Okay. Okay, I want to make a break here also because now I will just talk. All my talk is based on that. So I hope I was able to, for those not knowing the formalism, to capture a bit what's going on in this.
How for me to follow it. I just that when you say that we need complex number, but a complex number is by definition two real numbers with imaginary.
Yes.
I see that you try to.
Well, which I did. So
it was so fast.
So this is what I'm doing. This is, imagine that this is a 5 by 5 matrix. Now this is a 10 by 10 matrix. So I just take a Hilbert space of dimension 5 times a Hilbert space of dimension 2.
Yes, but
Conceptually, I did exactly that.
Conceptually, what does it mean? It's more my ignorance, sorry, it's with my ignorance. What did you do conceptually? Forget that complex number is made of two real numbers. So what is the additional assumption that you told it, but obviously it was too fast.
Yeah, so
to say that, no,
of course,
I'm not
a
going
complex
to
number.
that a complex number is two real numbers.
No, but a complex
Well,
number.
I want to tell more when I
So a complex number is two real numbers, but I want to do much more than this. I want to keep the structure of the Hilbert space. I want to keep the structure of the Hilbert space and the tensor product. So what you said, just replace all complex number with a couple of two real numbers. Then you don't have a vectoral space anymore, right? So I want to keep the structure. They are scalars.
You want that the dot product in your space is no longer the dot product in the complex number space.
No, I want to.
Otherwise, it would be the same.
The idea is we're not quite saying you can't do the complex numbers with real numbers. We're saying you cannot emulate complex Hilbert spaces with real Hilbert spaces.
Yes, especially this tensor product.
You can't get
Because of the dot product is not the same.
Yeah.
Yes, yes, this will be the problem. Yes, this will be the problem. Actually, I will show that. So what I have shown is that in that type of situation, actually you can. Okay, and the intuition one complex number is encoded in two real number works. And I gave you the exact way to do it through this formula. I gave you how to replace all these complex numbers by two real numbers. Because I start from a 5 by 5 matrix and I obtain a 10 by 10 matrix. So it's clear that I have double the dimension.
And you escape from this because you said that now the dot product that the natural dot product in real space is not the same as in complex.
No, it will be no.
In this experiment, he is capable of emulating a 5-dimensional complex Hilbert space by means of a 10-dimensional real Hilbert space.
So
But
here,
in general, that's not the case.
it works. Here, I can do it. There is no problem. Somewhere in my talk, I will tell you, oh, here I cannot do it anymore, and I will tell you why. For now, there is no problem. Okay? I have not proven any contradiction for now, any problem for now. So here I have just shown that there is a way for the detective to win. Okay, the experimentalist is trying, but it didn't work yet, right? And how the detective did, he basically doubled the dimension. And what is the exact intuition? To double the dimension, if you want a physical intuition of how he did it, he said, I start from my initial system of, let's say, dimension 5, and I consider an abstract additional particle, which is this triangle, which contains this information. What is the value of the square root of -1? And just by alternating between +I and -I with equal weights, it works because this box will first measure the value of the square root of -1, and depending on that value, apply the good measurement and everything is fine. Okay, so now let me go to a more complex experiment which could be invented by the experimentalist. So the experimentalist could go a bit further and try to construct a Bell-like experiment. So now two particles, one going for A, one going for B, right? So exactly the CHSH game. And find a well-designed system such that I obtain some probability distribution which cannot be explained by the detective. So again, there will always be a way for the detective to explain that type of experiment, whatever the state, whatever the measurement. And okay, so this is why I say that the intuition of last slide was important, because what the detective will do is exactly the same. So the detective will consider a new table. So imagine that this was dimension 5 and this was dimension 5. So this system was dimension 25. What the detective will do is to consider like the particle plus a flag. So now this is dimension 5 times 2, dimension 10. This is dimension 5 times 2, dimension 10. So the total system is dimension 100. Okay, so I go from 25 to 100. And this state actually corresponds to the whole system, the whole two systems, plus two flags, one sent to Alice, one sent to Bob, which are distributing the same information. So the two flags will either say to both Alice and Bob, or the value of the square root of -1 is plus I, or the two flags will say to both Alice and Bob, or the value of the square root of -1 is -I, right? So it's really this plus this. So over my hidden states of dimension 100, actually, I'm using only half of it, in which the value of the square root of -1 coincides for Alice and for Bob. And then, so actually, I will not write the measurements operator, but what Alice will do essentially is to measure the flag, look at what is the definition of the square root of -1, and then apply the correct measurement either with the definition plus I or the definition -I. Bob will do the same. And what is really important is that in the rules of quantum theory, if everybody conjugates I into -I everywhere in the universe, it's the same, right? It's some independent, like the theory is exactly the same. It would not work if A had one definition, let's say plus I, and B had the other definition, let's say -I. What is important is that everybody has the same definition, which is very intuitive mathematically, right? Because I minus I are the same if I stick to one of them everywhere. So what is very important is that these flags, they give a correlated definition of what is the square root of -1 everywhere. So from this, actually, you can invent a universal flag particle simulation. So imagine that you have the universe, the Big Bang at the very beginning, and there were created infinitely many flags going everywhere. Then from that, you can construct a real theory which will explain, again, everything with real numbers. So what we need to do is to find a situation where this infinitely many flag correlated flag situation is impossible. And actually, so I really considered a unique, like I consider the strategy for the detective, but there might be many other strategies, right? The detective might find a new strategy where maybe you have flags with of dimension 10, or maybe it's not even a flag strategy, it looks completely differently. So I really discussed a lot, one strategy for the detective to reproduce everything with real numbers, but there might be other strategies. So this is what we did. So let me first discuss this flag situation, but in a new experimental situation, which is the following. Convince you that it's hard to do it, and then discuss a bit beyond that. So imagine now that the experimentalist constructs some experiment like this. And imagine that the detective, so in this experiment, I have two sources of two particles each. One particle going to Alice, Bob receiving a particle from each of the source, and Charlie receiving one particle from one of the source. And what I assume is that these sources are completely independent. So somehow, when I do this, I'm refusing this Big Bang explanation. So I really say, no, actually, there is not a common origin somewhere which explains everything in a well-tuned way. I can really create new experiments in which I have two independent phenomena at the very beginning, right? These two sources are completely independent at the moment that I create them. And then what the experimentalist will ask is to the detective to find an explanation of the probability distribution which will be observed there with real number systems, but again, two independent systems. So if I do that, you see that I have a direct problem with this flag strategy. Because the detective, to make his flag strategy, he needs to find somewhere a physical way to send physical particles to everyone, sending the definition of the square root of -1. But this I cannot do because, well, imagine I add flags to all the particles, then I will have a correlated flag between A and B because of this particle. I will have a correlated flag between B and C because of this system, but B might receive flags indicating different definitions for the square root of -1. And in the formalism of quantum theory, this is a problem. There is no clear way to deal with that kind of case for Bob. So in that case, Bob really does not know what to do to try to reproduce, to mimic what is observed in that case. So this is really the problem in this with this strategy in that case. So this is the intuition, and now the question is how to find concrete states, right, and concrete measurements which will really reveal that problem. So this is what we did. So I will not go at all into the details because it's a bit technical, but really what we did was to propose states, 2 qubits, and measurements. So it's just the standard Pauli measurement, the bell state measurement, and some Pauli measurements. It's really close to the CHSF experiment, apart from the measurements performed by Bob. And what we have to do is that it's fully impossible to reproduce these statistics with real number matrices of any dimension, even in units.
I just want to make a comment for the people in the room. So what you have is in fact a small quantum network. So
Yes.
I know that you are working on quantum networks with Renou, and the kind of, so in quantum networks with 3 nodes, we will have what Marc-Olivier called the Bell state measurement, and then this is part of what we call the integral swapping in quantum network. Just to clarify this.
Yes. Okay. So very quickly, the proof technique. I will not go at all into the details, right? I have just these 2 sentences. So the proof technique is in 2 steps. First, we use what we call self-testing. And with this, we are able to show that actually, if there were a possibility for the detective to explain what we observe here with real number, then the detective must have used the flag simulation. So actually, from self-testing, we understood that the flag simulation, which I presented, is the unique simulation you can imagine. So it's an extremely strong statement, actually, because you could imagine a simulation using infinite dimensional system, but we could really prove that no, actually, there is a unique simulation which might work. It is the simulation where I double the dimension and I do this flag trick. And then, okay, so this intuition was coming from the previous slide, right? We also proved that actually this simulation cannot work, right? Because you have this problem for Bob receiving 2 different flags from the left and from the right. Okay, so I'm almost done. Let me try to interpret a bit what's going on here. So it's really an interpretation made by someone who knows and accepts complex number standard quantum theory. So the interpretation is that actually in standard quantum theory, you have complex numbers. So in particular, you have this I, and actually there is a lot of structure, a lot of properties coming from that. And this I distributes some universal information everywhere in the universe. Everywhere in the universe, somehow people have access to some common information for free, which is what is the value of the square root of -1. And this you can really directly relate it to cardinality, so to direct orientation. So because in quantum mechanics, we have what we call the Pauli matrices, which are about particle of dimension 2. and which are directly related to rotations to this direction of space x, y, z. And if I change the definition of the square root of -1, I keep x and z invariant and I reverse y into -1. So I reverse causality. So somehow everyone has for free some information about causality everywhere. But then if you are now trying to use real quantum theory, this information is not given for free. And you need to provide it physically in some way. And then these physical flags I described are the way to simulate this common information, which is present for free in this complex number quantum theory. Okay, this interpretation really relies on these mathematical axioms, this tensor product, etc. And it's really an open question to me. Okay, is this how meaningful is this interpretation, and is there a way to really understand it better, maybe by trying to replace this mathematical axiom by something a bit more physically motivated? Okay, so I'm done. I just wanted to conclude quickly with some open problem, which is not well posed, but which is very important in our community, and a lot of people are trying to understand that now. So I just presented the Bell theorem, and in the Bell theorem you have what we often call classical physics. So it's more classical logic, classical information when I can use this logical OR. And I have shown you that there is some incompatibility with some concrete experiment. And then, so imagine you are the detective on day one, you try to invent a theory compatible with R, doesn't work because the experimentalists show you some experiment. Then imagine on day two, you come with real quantum theory. Again, it will not work because the experimentalist on day two will construct a new experiment which rules out your theory. And then, so I have another work where we do the same, but with a new class of theory, which we call generalized bipartite entanglement, where again, the experimentalist is able to construct some experiment which rules out the detective theory. And the open question in our community is, how far can we go with this? So if we imagine a detective coming every day with a new theory of information, can we oppose to it every day an experiment in quantum theory which tells the detective that he or she is wrong, right, with the theory, the new invented theory, to the point that in the end we'll be able to exclude all alternative theory to quantum theory and be able to certify that quantum theory is valid, just by being able to reject all alternative theories of information. So again, this is not a well-posed question at all, right? But what we are trying to do is to first formalize that question and answer it. And actually, it's an extremely important question, both for fundamental physics, also for trying to find new theories. So we have a problem in physics to reconcile quantum mechanics and gravity. So it would somehow, such a theorem would give you a series of tests to understand in a situation, let's say, close to a black hole, because if quantum theory is not valid anymore, this test somewhere should fail. So if you are in a situation in which you believe that quantum theory is not valid, means that you just need to understand how this test will evolve to understand where there is a problem about quantum theory. And then it's also something extremely important for applications, actually, because if now you have a black box and you might have some eavesdropper trying to manipulate it, this test would just mean that if you check them and you look at these statistics and it works, then actually you understand well the physics of your black box, the physics of the information inside the black box, and there cannot be anyone manipulating this black box. You can really ensure it from your tests. And with this, yes, I'm done. So I just want to thank all my colleagues. And yes, if you have questions, I'm happy to answer it.
So, thank you. Any question in the room?
I can ask one. There's just one part I'm not quite sure I understand. When you give the functional group, the one that the detective cannot break, you have this idea that the two generators generate independent
Yes,
quantum particles
yes,
or pairs. But you said that your flags were everywhere. So they both already, the two generators have a flag. And I'm not sure I understand what the role of the flag, because I understood it as the flag is universal, in which case it applies to the generators.
yes. So
So what did I misunderstand?
yes, so if you want to reproduce complex quantum theory with real numbers, what we have actually proven now is that there is a unique way to do it, which is that there is some common information, which is the value of the square root of -1, and this common information is everywhere, and
heritage, not information, heritage.
well, let me call it some information, right? And this information is everywhere. And to perform any operation, you first measure that information. And depending on the value of that information, you apply either what you wanted to do or the conjugated version of what you wanted to do, right? It's really what I have written there. So to do that, there are several ways actually to physically model this. Either you say, oh, I have some physical particles which were sent everywhere and which contains that information. Okay, so it really corresponds to the drawing I have there, right? Or, okay, so actually there is some alternative, but this is when you invent a theory, you could say, okay, there is the physical space and somewhere else in some parallel universe, there is a qubit which contains that information and everybody measures that qubit and have access to it independently of the notion of space.
There is a common heritage, which is the time arrow.
Yes, but okay, you
Because,
could alternate.
The reverse time, it's exactly that you flag, you switch the flag square root of -1.
So there is no time in quantum information theory. There is no evolution, there is no time.
It's too easy for all stuff.
No, there is no
Ah,
time.
easy.
No, actually,
Like
it's a good point. So if you start to include the Schrödinger equation, this time reversal
No,
is important in the question.
But
if you want-
because you said at the very beginning, you must have some time.
No, yeah, well, it's an image. No,
Okay.
what is important in our proof is that we were able to prove it at the level of quantum information theory. We don't need dynamics. So it's really quantum information theory, it's not mechanics. Already at the level of quantum information theory, you have a problem with real quantum theory, and this was not so clear. So if you want quantum information theory comes first, and then you can add a dynamic, but you don't even need to consider dynamic to have problems. But okay, let me try to finish to answer the question. So if I come back to this drawing, right? Of course, there is an extension which works, which is to say there is the Big Bang. So let me represent it by a star there. And the Big Bang caused this particle, like this system and that system, and distributed, let's say, 1, 2, 3, 4 flags. And these flags are then sent like this and like that, and they are correlated. And this is a perfectly fine situation. However, if you start to just keep that kind of explanation, it means that there is nowhere in the universe two independent sources which are not linked in their past, right? So if you are fine with this, you can just say, this proof is bullshit because I believe that there is a common source everywhere for everything all the time. Our proof is valid only in the restricted assumption, in this extra assumption that you do have experiments in which you have independent sources. Because it's an assumption.
Yeah, it's an assumption. Because if you suppose that everybody has the same value for square root of -1, then that doesn't work, right?
Of course.
Okay.
Yes. But the point is that the theory enable you to describe this type of experiments with independent sources. Because in the theory, if I go back to the axioms, right, you have, if I have two particles, this is the same. And if I have independent preparation, it's associated to a tensor product like that. So if you take this point of view, this viewpoint saying, oh no, but there is a common path to everything and there is this value everywhere, just means that this assumption, this sentence is useless, right?
So we're not invalidating
Because
all of
it
point four.
never happens in practice. You can never do that, right? Because you never have independent preparation, right? So somehow in your theory, you have this tensor product rule, but you never use it in practice because for some deep physical reason, it will never happen.
And you can use the vocabularizer, so it is much simpler with imaginary quantum mechanics and you have this use the gas factory with the real numbers.
There are also other, if you include, so time is excluded, so we are very clear in your presentation. If you include the time evolution, then what you will have is, you can have some other arguments to say that, yes, we need, it's not only because of the HAL in the Schrödinger equation, because you can have a Schrödinger equation without the HAL, but you still need something that includes the complex number.
I was
Because-
advocate of the devil because
No. So it's a good point.
that with
with again,
numbers, it's much simpler.
this is the information theory. It's the cinematics. You don't have any equation of movement. If you try to include equation of movement, this is really painful. So there are a lot of reasons why real numbers are really not great. However, what is extremely new here in this result is that actually you don't need even any consideration about dynamics. It could be any dynamic, or there could be no dynamic in the universe, right? It will still work, right? It's encoded at the level of the quantum information theory that there is a problem, not at the level of the dynamic.
I'm still the advocate of the devil. At some moment, you said that Bell's theorem contradicts information theory. And information theory is even more agnostic of time. There is they don't care about dynamic. And
Okay.
as far as I understand from the past of Bell's theorem, it was the contradiction of the locality assumptions,
Yes.
which typically say that if you have two particles and you feel their common past, then they should behave independently. And
Yes.
of course, that's not the case with the Bell state. And but information theory, of course, allow, because you can do everything you want
Yes.
with information, to have a correlated information source. That's
No. So there is more structure in what I explained, right?
but it is not a contradiction of information theory. I mean.
Yes.
Local information.
Yes.
Yes, but that doesn't mean nothing, because information theory is something which is agnostic.
Yes.
No, I just say that.
No,
Otherwise,
of course.
if you mix the two.
No.
then-
So okay, maybe I said something wrong at some point, but
Yeah, would be wrong.
the arguments are. Yes.
The idea, yeah, you need temporality, you need the idea that if you can't communicate faster than light, that's going to restrict your information.
And you say also that the particle carrying information cannot go faster than light. I'm very happy with that. But there is something which is possible with information theory, that emptiness, a blank, nothing, is also information.
Mhm.
How you
No, so what is important
how
is
fast
signaling.
nothing.
What is important is signaling. It's not information, it's to signal something. So you have two locations in
Yes,
space,
it's signal.
and you want to send a signal from one location to another, right? And to send a signal, it means that you need to make a decision in the first location of space, and the result of that decision will have a direct impact in the second location of space. So if you are just using one type of message, blank message or any message, it doesn't work. You need to modify it in the first location of space.
But you wanted to say that there is a. I'm teaching a course about information theory, so I try to simplify, to oversimplify confusion, so in order to avoid the trap of information, the quantum information. I just tell them first you have signal, then you have data. Between signal and data you have measurement, and then after you have information. But it's why then when you reverse, that can be some confusion. Just for the terminology.
So any other question? I can go back to the Bell theorem also, or Yeah. If
On
it's-
the bridge, do you have some questions? In the room? I will have a last comment and I didn't, I was really interested in the one of your last ideas about the relation between chirality and the choice of the square root of -1. I didn't, for it's clear now, but I didn't have this in mind. And what is interesting is that, in my opinion, is that if you consider everywhere -I and you say that it is the true I,
Yes,
then the structure is exactly the same. In fact.
Yes.
You have exactly, you
Yes.
cannot distinguish
yes,
between them.
of course.
And but what is important is that everyone in
Yes,
the universe
exactly.
has the same
Yes.
direction. In fact.
Yes, 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 yes.
And this
Yeah, so
this
actually
is
I
something
tried
that I
Find
found
more
very interesting.
content and stuff to say behind this, and I discussed a bit, but I never, yeah. I have this intuition, but it's really.
It was just a
vague.
comment, and I really like this idea. In fact, and no, I understand the thing. I think a bit better what is chirality and the relation with the choice of the square root of -1. Yeah, it was just a comment. But, so no other questions. So thank you again. Merci.